Every car review highlights horsepower and fuel economy, but dealers never mention the catastrophic engine failures waiting just outside your warranty period. What if your brand new $50,000 SUV has an engine designed to self-destruct at 70,000 miles? That's not speculation. 3 major manufacturers are currently selling powertrains with documented defects that destroy themselves completely, leaving owners with $8,000 repair bills. Federal investigations confirm it. Class action lawsuits prove it. Your dream SUV might be the worst financial decision you'll ever make. In this video, I'm exposing the 3 engine platforms you need to avoid in 2025. The #1 choice is so widespread that hundreds of thousands are already on the road, ticking like time bombs. Watch every second, because this isn't just a review. This is the difference between smart car ownership and financial devastation. We're focusing on 3 specific engine platforms sold between 2021 and 2024. These aren't rare, exotic powertrains. These are mass-market engines installed in some of America's best-selling SUVs. Hundreds of thousands of these vehicles are on the road right now, and a significant percentage will experience complete engine failure. The scary part is that most owners have no idea what they're driving until the day their engine destroys itself on the highway. Number 3. The Nissan variable compression disaster. The Nissan Rogue compact SUV adopted a genuinely innovative engine starting in 2021. The 1.5-liter variable compression turbo 3-cylinder was marketed as a breakthrough in efficiency. Variable compression means the engine physically changes its compression ratio while running, switching between high compression for efficiency and low compression for power. On paper, it sounds incredible. In reality, it's a mechanical nightmare. This technology requires an intricate multi-link system with extremely tight tolerances. Everything needs to work perfectly, all the time, with precise lubrication hitting every critical surface. The system uses a complex arrangement of links and actuators to physically change the position of the crankshaft relative to the pistons, altering the compression ratio dynamically based on driving conditions. It's genuinely impressive engineering that demonstrates what's possible when you push the boundaries of internal combustion technology. The problem is that pushing boundaries often means finding new and expensive ways to fail. When this system doesn't receive perfect lubrication, when tolerances shift even slightly due to wear, when any component in the complex mechanical chain experiences stress beyond its design parameters, the engine doesn't just run poorly, it seizes completely. Owners have reported catastrophic failures at shockingly low mileages. We're talking engines with connecting rods punching through the oil pan at 15,000 miles. That's barely broken in for a normal engine. Some failures have occurred even earlier, with owners reporting total engine destruction before the first scheduled oil change. These failures require complete long block replacement, and the parts have been back-ordered for months at a time. That delay alone tells you everything about how widespread this problem has become. Nissan didn't anticipate needing this many replacement engines this quickly. The back-order situation creates a secondary nightmare for owners. Imagine your daily driver experiencing complete engine failure. You need this vehicle to get to work, to handle family responsibilities, to maintain your life. Now imagine being told that the replacement engine won't be available for 3 to 6 months. Nissan hasn't provided adequate loaner vehicles for all affected owners, meaning some people are stuck making car payments on a vehicle sitting dead in their driveway, while also needing to arrange alternative transportation. The official recall response from Nissan is particularly telling. When engines are literally destroying themselves from internal wear, the manufacturer's fix is an oil change, a gasket replacement, and a software update to enhance engine monitoring. Read that again. Software cannot fix mechanical wear. A computer update cannot restore components that have already experienced premature failure. An oil change doesn't address fundamental design flaws in the variable compression mechanism. This response suggests Nissan is managing warranty costs rather than addressing the fundamental design flaw. The software update likely adjusts monitoring parameters to detect failures earlier, potentially preventing some catastrophic damage by warning owners sooner. But it does nothing to prevent the underlying wear that causes the failure in the first place. It's a band-aid on a bullet wound. If you're considering a 2021 through 2023 Nissan Rogue, understand that you're gambling with one of the most mechanically unsound engines in its class. The complexity that was supposed to deliver great fuel economy instead delivers a high probability of complete engine destruction. This is innovation that actively harms consumers. The fuel economy gains, while measurable, are completely negated by the risk of total engine replacement. Even if only 20% of these engines fail catastrophically, those are terrible odds when the cost of failure equals or exceeds the remaining value of the vehicle. Number 2, Ford's double-threat EcoBoost problems. Ford's EcoBoost lineup faces something truly remarkable in the worst possible way. They're dealing with two completely separate, catastrophic defects across different engine families. This isn't one engineering mistake. This is a pattern suggesting systemic quality control failures across their entire SUV powertrain division. Let's start with the 2.0-liter EcoBoost 4-cylinder. This engine powers high-volume crossovers like the Ford Escape, Bronco Sport, and Lincoln Corsair. The defect is brutally simple. There's a fundamental flaw in either the engine block casting or the head gasket design that allows coolant to leak into places it should never go. Sometimes it enters the combustion chambers. Sometimes it contaminates the engine oil. Either scenario is catastrophic. Coolant in the oil destroys the engine's ability to lubricate itself. The coolant breaks down the oil's viscosity and creates a milky substance that cannot protect bearing surfaces. Internal components start grinding metal on metal. Main bearings fail. Rod bearings fail. The crankshaft scores. Within hundreds of miles of contamination, the engine suffers damage that makes rebuild impossible. You need a complete replacement. Coolant in the cylinders can hydraulically lock the engine or cause severe internal damage. Liquids don't compress like air does. When a piston tries to compress liquid coolant during the compression stroke, something has to give. Either the connecting rod bends, the piston cracks, or in extreme cases, the rod breaks completely and punches through the side of the block. This is immediate, catastrophic, irreparable damage. This failure typically appears around 100,000 miles, which sounds like decent longevity until you realize that's barely past the warranty period for a vehicle that should easily last twice that long. The timing is almost suspicious. It's as if the defect was engineered to appear just outside the coverage period, maximizing Ford's profit while minimizing their warranty liability. That's probably not intentional, but the effect is the same. Owners face massive repair bills right when they've finished paying off the vehicle and were hoping for years of reliable, payment-free transportation. The out-of-pocket cost for engine replacement ranges from $6,000 to $8,000. Ford has issued various customer satisfaction programs and partial recalls, but they haven't solved the core block defect. The fundamental design flaw remains. Some owners receive goodwill assistance where Ford covers a portion of the repair cost, but this is inconsistent and often requires extensive negotiation. Owners are left hoping their specific engine might be one of the lucky ones that doesn't fail, which is a terrible position for anyone who just spent $30,000 to $40,000 on a vehicle. The second EcoBoost disaster affects the larger V6 engines, specifically the 2.7-liter and 3.0-liter variants found in the Ford Explorer, Edge, Lincoln Aviator, and Nautilus. These are premium vehicles with premium price tags. The Explorer is one of Ford's best-selling vehicles. The Aviator and Nautilus are luxury products that command significant premiums. These aren't budget vehicles where you might expect some corner cutting. These are expensive SUVs where buyers reasonably expect quality and reliability. The defect involves faulty intake valves that are prone to fracturing. The root cause appears to be inadequate material quality or manufacturing defects in the valve stems. Under the stress of normal operation, these valves develop cracks that propagate until the valve breaks completely. When an intake valve fractures, it doesn't just stop working. The broken piece falls directly into the combustion chamber while the piston is moving at thousands of cycles per minute. The piston immediately hits the valve fragment, destroying both the piston and the cylinder head. The piston crown shatters. The valve fragment embeds in the piston. Metal debris circulates through the entire engine. Cylinder walls get scored. Other pistons get damaged. The cylinder head sustains damage so severe that it cannot be resurfaced. it's instantaneous terminal engine failure. As of August 2024, Ford acknowledged over 800 warranty claims specifically related to fractured intake valves in these engines. That's 800 documented cases where owners experienced this specific failure mode. The actual number of failures is likely higher, as not all owners file warranty claims, and some failures occur outside the warranty period where owners pay out of pocket and never enter Ford's warranty database. The recall remedy is particularly revealing. Ford requires dealers to inspect engines based on cumulative engine cycles. If the vehicle fails inspection, the entire engine must be replaced. Not just the valves, the entire engine assembly. That tells you how severe the collateral damage is when these valves fail. The fracturing component destroys so much of the surrounding engine that partial repairs aren't viable. You can't just replace the damaged cylinder's components. The contamination and damage spread throughout the entire power plant. Here's what makes this situation uniquely problematic. Ford buyers with these EcoBoost engines are exposed to two completely unrelated ways their engine can catastrophically fail. You could get the coolant intrusion design flaw, or you could get the fractured valve quality defect. It's almost impressive how they've managed to create redundant paths to complete engine destruction in the same model lineup. If you're shopping for a used Explorer, you need to worry about whether it has the block defect, whether it has the valve defect, and whether all recall work was properly completed. Beyond these two major failures, EcoBoost engines also suffer from the typical problems associated with turbocharged gasoline direct injection. Carbon deposits accumulate on the intake valves because there's no fuel washing over them. This leads to misfires and drivability issues that require invasive cleaning procedures like walnut blasting. That's an additional maintenance cost most owners never anticipated. The walnut blasting procedure involves removing the intake manifold, sealing the intake ports, and using compressed air to blast crushed walnut shells at the valve backs to remove carbon deposits. It's labor-intensive and expensive. Ford has historical patterns here too. The 3.5-liter EcoBoost used in larger SUVs, like the Expedition, had an internal water pump design where pump failure meant coolant entered the engine oil. The repair required complete engine removal, costing thousands of dollars. This establishes a clear pattern of expensive engine integration flaws that Ford seems unable or unwilling to engineer away. It's not like Ford doesn't know how to build reliable engines. Their naturally aspirated V8s and V6s from previous generations were generally solid, but the EcoBoost program has been plagued with expensive, catastrophic issues since its introduction. If you own one of these EcoBoost vehicles, especially the 2021 and 2022 models with the V6, you need to verify that any recall work has been completed. If you're considering buying one used, demand documentation of the recall service. Without it, you're purchasing a known defective engine that could destroy itself without warning. Don't accept verbal assurances. Get the service records showing the recall work was performed. If the seller can't provide that documentation, walk away. There are plenty of other SUVs that don't carry this level of catastrophic risk. Before we get to the #1 most unreliable engine, if you want to avoid making expensive mistakes with your next vehicle purchase, hit that subscribe button. We cut through the marketing nonsense and give you the real information manufacturers don't want you to know. Number 1. GM's V8 cylinder deactivation catastrophe. The top spot belongs to General Motors and their family of V8 engines, equipped with active fuel management and dynamic fuel management. This isn't just the most unreliable engine platform currently sold. It's also the most widespread, affecting the entire lineup of GM's full-size, body-on-frame SUVs. We're talking about the Chevrolet Tahoe and Suburban, GMC Yukon and Yukon XL, including Denali trims, and the Cadillac Escalade and Escalade ESV. These are high-margin, expensive vehicles that represent GM's most profitable segment. They're also equipped with engines featuring a defect so severe and so common that it's spawned federal investigations and multiple class action lawsuits covering vehicles built since 2014. The problem persists through the 2024 model year. Think about that. GM has been aware of this defect for over a decade, and they're still installing these engines in new vehicles rolling off the assembly line today. The engines in question are the L87 6.2-liter V8 and the L84 and L83 5.3-liter V8s. All of them use cylinder deactivation systems designed to improve fuel economy. The concept is straightforward. During light load or cruising, the engine control module shuts down cylinders. The newest dynamic fuel management system can deactivate up to 7 out of 8 cylinders. In theory, this saves fuel. In practice, it destroys engines. The fuel savings are accomplished through highly intricate, oil pressure-activated collapsible roller lifters. These components are exponentially more complex than traditional solid lifters. A solid lifter is a simple mechanical component with no moving parts. It's essentially a hardened steel cylinder that transfers motion from the camshaft lobe to the pushrod. Simple, reliable, proven over millions of engines and billions of miles. The collapsible lifters used in AFM and DFM systems have internal mechanisms that allow them to collapse when oil pressure is applied, effectively disconnecting the valve from the camshaft's motion. This requires precision machining, internal springs, check valves, and oil galleries. Each lifter becomes a complex hydraulic actuator rather than a simple mechanical component. Complexity in high-stress mechanical systems always creates vulnerability, and these lifters fail with remarkable consistency. When these lifters malfunction, they fail to collapse or extend properly. This creates excessive friction and wear, leading to eventual seizing. The first symptom owners notice is usually a persistent ticking noise from the valve train. This is the sound of a lifter that's not maintaining proper clearance, creating metal-to-metal contact. Then come misfires, reduced power, and rough idling. If you keep driving at this point, which many people do because the vehicle still technically runs, the failed lifter damages the corresponding camshaft lobe. The camshaft is made from hardened steel, but it's designed to work with lifters that maintain proper contact and lubrication. When a failed lifter starts hammering on the cam lobe with improper contact patterns and inadequate lubrication, it wears the hardened surface away. The lobe develops flat spots. The valve timing for that cylinder becomes erratic. Engine performance degrades further. This is where the situation goes from expensive to catastrophic. The damaged camshaft and lifter generate metallic debris that circulates throughout the entire engine in the oil. That debris acts like sandpaper on every internal surface. Bearings, cylinder walls, and other critical components start wearing rapidly. The oil filter catches some of this debris, but not all of it. The smallest particles pass through the filter and continue circulating, accelerating wear on every lubricated surface in the engine. Eventually, the engine seizes completely, requiring total replacement. Bearings fail, the crankshaft locks up, pistons score the cylinder wall so badly that the block cannot be reused. You need a complete long block assembly, and you need a skilled technician to install it properly. This is not a shade tree mechanic repair. This requires dealership-level equipment and expertise. The estimated fuel economy improvement from this technology is 5 to 7%. That's what GM decided was worth engineering a system that routinely destroys engines worth $8,000 or more to replace. Let's do the math on that. If you drive 15,000 miles per year and average 18 miles per gallon, you're using about 833 gallons annually. At $4 per gallon, that's $3,300 in fuel costs. A 7% improvement saves you $230 per year. Over 5 years, you save $1,150 in fuel costs, but the system that saves you that $1,150 has a significant probability of causing an $8,000 engine failure. The math doesn't work even if the system worked perfectly, which it demonstrably does not. This is a perfect example of efficiency engineering creating a net financial loss for consumers. Out-of-warranty costs for this failure start at $2,500 to $4,500 just for lifter replacement. That's assuming you catch it early before the camshaft is damaged. If the camshaft needs replacement too, you're looking at higher costs because the labor to access the camshaft is substantial. The entire front of the engine needs to be disassembled. If the engine has ingested metal debris from a catastrophic failure, you're looking at complete engine overhaul or replacement, frequently costing $5,000 to $8,000 or more. The problem is so widespread and the failure rate so predictable that the aftermarket developed a simple solution: A plug-in device that connects to the OBD2 port can permanently disable the cylinder deactivation system. This forces the engine to run in full V8 mode constantly, preventing the computer from activating the collapsible lifters. No lifter activation means no lifter failure. The lifters remain in their extended position permanently, functioning essentially like traditional solid lifters. These devices cost between $40 and $100. That's the price of preventing a failure that costs 50 to 80 times more to repair. If you own one of these GM V8 SUVs and you haven't installed a cylinder deactivation disable device, you're gambling with thousands of dollars for absolutely no reason. The minimal fuel economy reduction from running in V8 mode all the time is completely negligible compared to the cost of engine replacement. You'll lose that 5 to 7% fuel economy benefit, costing you maybe $250 per year in additional fuel costs. That's a bargain compared to an $8,000 engine replacement. What makes this situation particularly egregious is that GM has known about this problem for years. The active fuel management system has been causing failures since 2014. They've had a decade to engineer a reliable solution, and instead they introduced dynamic fuel management, which is the same concept with even more complexity. They took a system that was already failing and made it more complicated. DFM can deactivate more cylinders in more combinations than AFM, which means even more complex control strategies and even more opportunities for lifter failures. The National Highway Traffic Safety Administration has launched investigations. Class action lawsuits are proceeding. Owner complaints number in the thousands. Online forums dedicated to these vehicles have hundreds of pages of owners discussing their lifter failures, sharing diagnostic tips, and warning potential buyers. The evidence is overwhelming and publicly available. Yet GM continues to install these engines in new vehicles. GM's response has been inadequate warranty extensions in some cases and continued production of engines with the same fundamental design flaw. Some owners have received goodwill repairs outside warranty, but this is inconsistent and often requires extensive negotiation, social media pressure, or legal threats. The extended warranties GM has offered on some model years don't cover all affected vehicles and still expire well before the typical lifespan of these expensive SUVs. For anyone considering one of these vehicles, understand what you're buying. You're purchasing an expensive SUV with a known defective engine that will likely need major repair or replacement shortly after the warranty expires. The only responsible action is to immediately install a cylinder deactivation disable device and accept the minor fuel economy penalty. It's not optional. It's mandatory preventive maintenance for a design flaw the manufacturer refuses to fix. If you're looking at used examples of these SUVs, factor the cost of the disabler device into your purchase price and install it immediately. Don't wait for symptoms to appear. By the time you hear the ticking noise, damage may already be occurring. Prevention is exponentially cheaper than repair. Speaking of reliability, if you want to know which older vehicles actually deliver on their promises of longevity, check out my video on 20 old cars from the 2000s that were built to last forever. These are the vehicles that prove manufacturers once knew how to build engines right.